change in topic. We're going to talk about a new thing called the matrix inverse in this lesson, and it is an extremely important concept. And I want to motivate it by going back to something you probably did in middle school or high school, and that is solving systems of simultaneous equations. So if you remember that, you were given equations that had x, y, and z, or some variables in there. And what you had to do was say, what values of x, y, and z can you have that will make all of the equations simultaneously true? I don't know about you, but I used to hate those problems. And I found them extremely tedious and error-prone. And luckily, linear algebra is going to come to our rescue and be able to make this much easier. So let's just kind of review what this looks like, right? So maybe this is the first equation you got kind of early in your career. And you were supposed to solve it, and you did, and that was pretty easy, right? Because if you divide both sides by 4, you end up with negative 2 for x. This is one equation, one unknown. And then you moved on to 2 equations, 2 unknowns. So, and when I say unknown, I mean variable. Maybe you call it 2 equations, 2 variables, right? And in this one, you had to say, okay, what am I going to do? And there's various ways of solving this. The way that I always liked most of all, which was sort of the least of evils, was to get one variable in terms of the others. So I look at that first equation and I solve it for x by adding 3y to both sides and then dividing both sides by 2. And remember, we can always do the same thing to both sides of an equation and end up with a valid equation, because if the two things are equal to each other before we perform the identical operation, they're obviously going to be the same after we perform the identical operation. So if we add 3y to both sides and then divide by 2 on both sides, we end up with that. And then we stick that value for x in the second equation. So I've just replaced the x in the second black equation up there with our little thing we found out it was equal to from the first equation. And then you do all your bookkeeping and you solve for y, and you end up saying, okay, y equals 1 and x equals 2. And this is where you always go back and check your work, right? So if you plug x equals 2 and y equals 1 back into both those equations, you should end up getting a correct statement. So 2 times 2 minus 3 times 1 is 1. That's true. And 3 times 2 plus 1 is 7. That's true. And maybe your math teacher tortured you by going further and saying, wow, let's have 3 equations, 3 unknowns. And in fact, you can go to 1 million equations, 1 million unknowns, and believe it or not, people actually do that to solve certain applied problems. They don't, however, crank through all this algebra by hand. They're going to do the trick that we learned in this lesson. But anyway, if you do lots of steps here, which I'll omit, because they're extremely long and tedious and very error-prone. I can't do one this size even without screwing up somewhere. You end up with the magic answer that, and x is negative 1 and y is 5 and z is 2. And so that's how you're able to solve those using the middle school and high school tools that you have before you learn linear algebra, right? And by the way, it may have struck you as interesting. It certainly did me in the midst of all the minutia of gathering terms and dividing by this, that, and the other and distributing whatever. It occurred to me, you get that answer, but you might ask, I wonder if that's the only answer, right? So we know on that last one that x equals negative 1, y equals 5, z equals 2, makes all those equations true, fun fact. But is there any other set of 3 numbers? And you might realize, based on what we've talked about before in this volume, that that's not the case, that there will not be more than one solution, and it comes exactly down to that blue versus yellow dominoes thing, as we will see in a little bit. But what I want to talk about now is not that deeper question of, is there more than one answer? Although we'll talk about that a little bit later. Right now I want to talk about a simpler way to get the answer using linear algebra. Okay? So what I want to do is I want to cast this as a matrix problem. Okay? So consider, let's say we have, these are our 2 equations, 2 unknowns. 2x plus y equals 5, and 4x minus 2y equals negative 2. Okay. We know we can go through all the algebra to do it. But I want you to consider this. I'm going to make a little matrix here. And I'm going to make a vector here. And I'm going to make this equal to another vector here. And I'm going to write this. 2, 1, 4, negative 2. And I'm going to write 5, negative 2 over here. And I'm going to write x and y right here. And I want you to stare at this. And I want you to stare at it hard. And I want you to realize that these 2 things are exactly the same. I've just expressed it in terms of matrices. Because look at this. If we take this dot producted with this, we get 2 times x plus 1 times y, right? 2 times x plus 1 times y. And 1 times y, of course, is the same as just y. So I could just write y here. And similarly, if we do the bottom row times that thing, we get 4x minus 2y. So this matrix vector product gives us these two things which are equation-y, right? And then it won't surprise you to know that if 2x plus y, 4x minus 2y, if that vector is equal to the vector 5, negative 2, then that's just another way of saying that 2x plus y is 5, and 4x minus 2y is negative 2, right? Because the only way we could have this left-hand vector equal to the right-hand vector is, duh, if this top thing is equal to 5, and if this bottom thing is equal to negative 2. So what we've discovered here is that this thing cast in matrix form asserts exactly the same thing as these equations up here, okay? Now, here's what we want to do, and this is where the critical step comes in for this episode. I'm going to rewrite this here. 2, 1, 4, negative 2 times the vector x, y equals the vector 5, negative 2. Now, what we'd like to be able to do, and this would be super cool. Actually, let me write this a little bit different. I'm going to give myself a little bit more room on the right-hand side here for reasons that you'll see. Equals 5, negative 2. What we'd like to do is get this whole thing to instead say just plain xy equals something, something, right? Because if we could get this, then we've solved the problem. We know that x equals that something and y equals that something. So our ultimate goal is just to get x and y over here on the left. And in order to do that, we have to get that guy to go away. What we want is to get that guy to go away. So the question is, how do we get that guy to go away? And here's the answer. We want to multiply this by some matrix, and I'll tell you right now it's going to be a 2 by 2, even though that might not be super obvious, but it is going to be a 2 by 2 for us. We want to multiply this by a 2 by 2, and of course, in order to make this a valid equation, we also have to multiply this side by 2 by 2, right? The same 2 by 2, because we know that if we have an equation, we can do the same thing to the left-hand side as we do the right-hand side. So if we left multiply this whole black thing by some green matrix, and then we left multiply this black thing by the same green matrix, we're guaranteed to have a valid solution here, right? So the question is, what do we need this thing to turn out to be? And the answer, you may realize, is this. We looked at this in the quick review stuff from the last segment. This here is called the identity matrix, as we know. And the identity matrix times anything is that thing, right? If I end up having 1, 0, 0, 1, and I multiply this by 2, negative 9, then I get 1, 0, dot producted with 2, negative 9 is 2. 0, 1, dot producted with 2, negative 9 is negative 9, right? So we get the same thing out. Therefore, if we multiply 1, 0, 0, 1 by xy, then we are in fact going to get just plain xy. So this is exactly what we want. And then whatever this green guy is over here, we'll multiply by 5, negative 2 and get our answer. Now, the question, and this is the $64,000 question, is what do I need to multiply it by in order to get 1, 0, 0, 1? What matrix can I multiply A by, we're going to call this A, this matrix here is A, to get the identity matrix I? That is the key thing. And the matrix that can do that is called the inverse of A. Okay? So the inverse of a matrix is another matrix which you can multiply by it to get the identity matrix. And the reason that's useful is because then we can get x, y, or however many variables we have. If it's 3 equations, 3 unknowns, or 50 equations, 50 unknowns. We can get just plain x, y, z, yada, 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 equals the right thing on the right-hand side. We have to be able to get the identity matrix so that multiplying the identity matrix by xy, the identity matrix goes away and we just get xy. So we need to multiply that left-hand matrix by something which will give us the identity matrix, and that is called the inverse. Now, figuring out what the inverse is extremely complex, and luckily for us, we're going to do it by computer. For right now, I'm just going to tell you, I assert, this is Stephen just flat telling you, that A inverse, and by the way, that's the notation we're going to use, that's read A inverse, which means the inverse of the A matrix. I'm going to state that in this case, we knew that A was 2, 1, 4, negative 2. That is A. I'm just going to tell you A inverse is, believe it or not, 1/4, 1/8, 1/2, negative 1/4. What? Yeah, that's what it is. Now, you can stare at this all day to try to see the pattern, and you probably won't be able to because it's actually not that obvious a pattern. What you can do, though, is you could check me to make sure this does actually multiply out that way. So let's see if we can do that. If we multiply A times A inverse, we get 2, 1 dot producted with 1/4, 1/2. That's going to be 2 times 1/4, which is 1/2, plus 1/2. That gives us 1. 2, 1 dot producted with that thing is going to give us 2 divided by 8 is 1/4 minus 1/4, so that's 0. And then you do the same thing here. 4 minus 2 times that, I bet you get 0. And 4 negative 2 dot producted with that, I bet you get 1. And so lo and behold, you get the thing out here like this, right? Now again, figuring out what the inverse of a matrix is turns out to be a complex computation that the computer is going to take care of us for. We're going to learn how to do that in R and Python's lickety-split. And in fact, in real life, nobody does the matrix inverse by themselves, by hand, right? They use a calculator or they use a computer to figure it out. One open question that I'm going to leave sort of sitting there until next segment is this. Does every matrix have an inverse? Interesting thought. Does every matrix have an inverse? And we'll talk more about that when we get to the next segment. But just to finish up this problem here, right? So now that I've told you that the inverse is, and you just believe me that I figured this out, and you checked me to make sure that it does add up to, or multiplied by the original A, does in fact give us the identity matrix. Here's what we can do. 2, 1, 4, negative 2, x, y, equals 5, negative 2. So let's take our blue guy, at least it's blue right now. Oh, I guess it's red. 1/4, 1/8, 1/2, negative 1/4. And then over here, 1/4, 1/8, 1/2, negative 1/4. And we're going to multiply these guys together. Now, if you take that times that, and that times that, that's what we did the last slide, right? You do all that stuff, and you know that we get 1001. So right now we've got 1001 times xy equals this thing times 5, negative 2. And we know that anything times the identity matrix is itself, so this actually just reduces to plain old x, y. And so now all we have to do is do this product. That guy times this, and that guy dot producted with this. So if we do it, we say, what's 1/4 times 5? That's 5/4. Minus 1/8 times 2, that's minus 1/4. So 5/4 minus 1/4 gives us 1. And then if we take 1/2 times 5, that's 5/2, minus 2 over 1/4. You work that out, you end up getting 3. And so we have now solved this system of simultaneous equations, x equals 1, y equals 3. And if you plug that back into your original thing, which was 2x plus y equals 5, and 4x minus 2y equals negative 2, you will discover that lo and behold, we got the correct answer there, right? So, big point here is that there is a purpose for an inverse. Turns out there's a lot of purposes for it that we're going to touch on. But the first one we're going to learn is just sort of motivated by this simultaneous equation thing. We can figure out how to do any simultaneous equation thing without doing the algebra, without cranking through all those error-prone solve for this and add this many times this equation plus this other one to get this other one and substitute your variables and distribute the minus sign and don't forget you moved it to the other side so make it negative, blah, 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 blah. All that kind of stuff we can get rid of and simply replace it with a single matrix operation. We make the matrix, we say, give me the inverse, multiply it by the constants that I have on the right-hand side, and I've got my answer. Okay? And that works for any number of dimensions here. So another example would be, suppose we had 6x plus 2y minus 4z. This was the last one I had in that little slide set, which I told you would be a lot of steps to do, right? Well, guess what? Now it's 2 steps, like everything else is. 2y plus 8z equals 4. All we have to do is cast this in matrix form, which is 6, 2, minus 4, 1, 1, 2, 2, negative 2, 8 times x, y, z equals negative 4, 8, 4. Now, by the way, just before I continue to crank this out, notice if it had said something like this, notice if we said, what if it was 6x minus 4z equals negative 4? Hopefully it's obvious to you. I would have had to make this first row here be a 6, 0, negative 4, right? Because if you're missing any variables here, that simply means that that variable is really 0, because what I'm saying here is 6x plus 0y minus 4z, right? So don't mess that up. Don't take this 6, negative 4 and make it be 6, negative 4, because that would be wrong, right? It's got to be 6, 0, negative 4, okay? All right, so we don't have 0. In this example, we actually have a non-zero value here, but just so you don't mess that up in case you get an example like that. Okay. Now, again, we have to ask the oracle. We have to go to Stephen and say, hey, Stephen, what is the inverse of that matrix there? And Stephen says, I'm glad you asked. You may not believe me, but the inverse is this. 3/10, negative 1/10, and then 1/10, and then negative 1/20, and then 7/10, and then negative 1/5. I know what you're thinking. You're like, where the heck did he pull this out of? Negative 1/20. 1/5. That's why it's good to have computers to do it for us. 1/20. That right there, ladies and gentlemen, is the inverse of this, which means if I took this blue thing and I multiply this matrix by it, and that wouldn't be a bad idea to practice, so you get your you get some confidence about this, and also you do some more practice with matrix multiplication, you are going to get 1 0 0 0 1 0 0 0 1, which is the identity matrix. That times xyz is going to be just xyz, because you multiply anything by the identity matrix, you get the same thing back. And therefore, all we have to do is take this big thing and multiply it by this, which maybe seems hard, but it's not nearly as hard as all these steps of algebra would have been. And when we do that, we end up getting x equals negative 1, y equals 5, and z equals 4. Because this whole thing turns out to be on the left-hand side, the vector minus 1, 5, 4. All right? So, simultaneous equations, you can solve them the old-fashioned way, or you can solve them by taking advantage of the matrix inverse, which is one of many, many, many useful properties of that particular operation.